Today it is time to learn about improper integrals, okay? And this is a topic that I think comes up in every Calculus 2 class at some point, and now is our time to do it. And like with anything, I can just cut to the chase and tell you how it works, but I want to encourage you to understand what's happening the best I can. And so I'm going to have you, before I tell you how it works and how you get the answer and all that kind of stuff, I'm just going to get you to try to think about something, all right? So can you think about this integral? It says the definite integral from 1 to infinity of 1 over x squared dx, okay? So think about that. At first glance, what would seem new or unique about this integral is that upper bound there being infinity. Okay, so here's how I want you to think about it. You can think of that integral as the area under this curve from 1 to infinity, okay? And this curve has a horizontal asymptote on the x-axis. So you see this little amount of space right there? As you go out further and further and further, that tiny amount of space gets smaller, but it never completely closes. There's always something there, okay? All right, so that's how you can think initially about what this integral could mean. Because if I don't show you this picture, it's just an integral. If I show you the picture, then you have something to think about to go along with it, all right? So suppose that you understand that and you make this association between the integral and this area here from 1 to infinity, okay? So here's the big question. Could this area be finite? All right. The region that the integral represents, from 1 to infinity, that's unbounded because remember, I told you this, if you kept going out further and further, there's always a little bit of space between the curve and the x-axis. So to me, that's why that's sort of a big question about this, is could that be finite? I mean, it is unbounded. The region itself can't be contained, but could the actual area measurement be finite? I think most people would say, of course it can't be finite. This stretches out forever. There's always a little bit of space there. If you measured the area, how could that possibly be finite? All right, I think that's what most people would think if, at least initially when they hear about this. All right, but so let's try to answer this question. How do you work this integral? How could you measure the area under this curve from 1 to infinity? So here's the first approach to doing that I want to show you. Okay? The problem with this integral is infinity is not a number. 1 is obviously a number, but infinity isn't. So if I was going to calculate this by the fundamental theorem of calculus, then here would be the process. I would find the antiderivative of the function 1 over x squared, and I would put in the bounds, the upper and lower limits of integration, and I would do a calculation. But how are you going to put infinity in and do a calculation? I mean, I can see you can put 1 in, and you can do the math, but there's no infinity button here. All right? Infinity is not a number. So how about this? Let's try to do it like this. Since I can't really reach all the way to infinity, it's not a number suitable for calculation, then let's say I'll go from 1 to 10. So say if I work this integral out from 1 to 10, I'll get 0.9. Okay? With the fundamental theorem of calculus. And now I'm trying to get a glimpse of infinity. So then I'll go from 1 to 100, and I'll work the integral again, 0.99. Okay, so I'm trying to get to infinity, so I'll go a little further, 1 to 1,000. And I work this integral with the fundamental theorem of calculus. I find the antiderivative, I put in 1,000, I put in 1, I do the math, I'll get 0.999. Do you see a pattern? It looks like the larger I make this upper limit of integration, the closer the value of the integral gets to 1, right? Can we agree about the pattern? 0.9, 0.99, 0.999. I think, any sane person would believe that if I bump that up with another 0, make it a little bit bigger, I'm going to get another 9 right there. So it does seem that the value of this integral is 1. Okay? Now, for many people, this is a real mystery, okay? Because what did we say? We said the integral from 1 to infinity, 1 over x squared dx, would correspond to the area under this curve from 1 to infinity, and that is unbounded. There is always a little bit of space right there. How could this integral possibly be finite? Not only is it finite, but it's 1, and so the physical area here under that curve from 1 to infinity is the same size as a 1 by 1 square. A 1 by 1 square, that's not unbounded. Like, I can hold that. But, how do you hold this if it goes from 1 to infinity? So it really is a kind of a paradox. It's very surprising to many people that the value of that integral could be a finite number. And in fact, it turns out that it's 1. All right? Okay. So I really do think that does seem amazing, that this has a finite area measurement to it, even though it's unbounded. All right, so that's some philosophical stuff for you to understand before we get started actually doing the work, okay? But I think that's an important jumping off point to understand this topic. Okay, so let's do this. The title of my video was Improper Integrals. I think at this point, we need to think about, okay, so if we're going to work these problems, and they're called improper integrals, what is an improper integral? Okay, so here we go. Here's the definition. An integral is improper if any of the limits of integration are infinity or negative infinity. So I see like that right there would make this particular integral improper. And that right there would make this integral improper. Just the presence of the infinities, okay? All right, and what would the infinities do? Well, it'd be recreating this situation here where you've got this unbounded space. And you could think the integral is trying to measure the area of this unbounded space, paradoxically. So that's one type of improper integral. Another type of improper integral that'll be a little bit harder to notice, but I think that you'll be able to do it, is that if one of the limits of integration causes or leads to a vertical asymptote on the graph of this function. So I'll give you this example. So you have the integral from 1 to 4, 1 over x minus 1 dx, okay? There, on this graph, all right, 1 over x minus 1, it looks like this. There's more of it over here, but the integral was 1 to 4, all right? So it looks like this. And there's nothing wrong with the 4, all right? Because there's the 4 right there. You'll get this point. What's the y-coordinate at that point? It's 1/3. But at 1, there's a vertical asymptote. The curve goes to infinity as you go to 1 from the right, okay? So the vertical asymptote makes the region unbounded in the same way that that first problem I showed you was unbounded. I mean, if you just turned this picture on its side, that would look like a vertical asymptote. So that's what makes improper integrals, okay? So either we'll just directly have infinity as one of our limits of integration, or one of the limits of integration corresponds to a vertical asymptote on the graph of that function, whatever it may be, okay? All right, so now that's how you recognize them when you see them. let's look at some examples. In this video, I think I'm just going to stick to this first type, and then I'll cover this second type in another video. All right, so here goes. So let's see. This integral is obviously improper because of that upper limit of integration being infinity. Okay, so here's the procedure for doing this. Infinity is not a number suitable for calculation. It just isn't. How did we do that first problem I showed you? I said, well, I want to do this integral 1 to infinity. I can't exactly plug infinity in, but I could do like 1 to 10, and then 1 to 100, and then 1 to 1,000, and I could see a pattern. That's basically a limit. I'm pushing this upper limit of integration to infinity, and I'm going to see what happens. So whenever we see an improper integral like this, we replace this upper bound with a number that's under our control. Let's call that number b. And then we'll push that number where we want it to go, which is to infinity. Okay? Since I can't just plug infinity in, the most I can do is reach closer and closer to it. You can think of it like that. All right. So that's how I'm going to rephrase this integral. Basically, I just need to replace the infinity with a b. B is a number that I'm controlling. I'll push b to infinity. From here, you do these integrals with the fundamental theorem of calculus. Okay? And so here's what I mean. I need to find the antiderivative of this. Okay? Which is, so we got -3. We can look at this like x to the minus 3 power. So I'll get -1 over 2x squared. Okay? There's my antiderivative of that. Okay. So can we agree about that? But again, my limits are 2 to b. And I want to push the b to infinity. Okay? All right. So it's like, with besides the limit being involved in this, it's like evaluating any other definite integral. We use the fundamental theorem of calculus with the limits of integration and the antiderivative, but there's that limit involved in it. Okay? All right. So once we get this far with the fundamental theorem of calculus, what do? We put in the upper limit of integration. Okay? That would be this number b. I get -1 over 2b squared minus, and then I put in this lower limit of integration. And when I put 2 into that, I'm going to get -1 over 8. Okay. And then I calculate this. It's just that I can't really just plug infinity in and square it and so on and tell you what I get. So I'm going to have to, in order to figure this one out, I'm going to have to say, okay, what happens to -1 over 2b squared if b goes to infinity? If b goes to infinity, this number is very big. And you're dividing 1 by a very big number. The larger number you divide by, the closer to 0 your answer is going to be. This limit here is 0. So I'm going to get 0 plus 1 over 8. Or 1 over 8. There's the value of my integral. Okay? All right, so that's how it's done. I know you already know the fundamental theorem of calculus. The only other thing involved in it is this limit. Now, limits, that might be something that we need to review a little bit. Limits are something you learn in Calculus 1. If that's the part you're just really having trouble with, then I can make some other videos to review a little bit more about that. And some of the harder problems, I'm going to end up reviewing it anyway. I want to show you something real quick. All right, I've done the problem, but I want the problem to have meaning to it. So this curve here looks a lot like that very first one I showed you. Okay, it's got horizontal asymptote here on the x-axis. And I'm just saying, you know, the meaning and the result here of this problem is if you measured the area under this curve, 1 over x to the third power, from 2 to infinity, it would be finite, you know? So like the area here is like 1/8 of a square unit, whatever your scales is, you know, feet or centimeters or whatever happens to be, okay? So that's how big that is. Even though this is unbounded, even though this little sliver of space stretches out to infinity, it's still finite in its overall size, all right? Okay, now one more thing. When we evaluate an improper integral and we get a finite number, we say that the interval or the integral converges. Okay? All right. If I got infinity there, then I wouldn't say it converged. But if I get a finite number of any kind, I say it converges. Okay, so this particular improper integral converges. Let's look at another problem. All right? Okay, so this one again has an infinity as the upper limit of integration. Obviously, that's going to make it, according to what I've been telling you, that's going to make it improper. So let's see, how can we do this one? Well, remember, it has a lot in common with that one. My first step is to replace this upper limit of integration with a number that I can control. Infinity is not a number. I cannot plug it into anything. So I'm going to have to say what I need is to do the limit as b goes to infinity. 1 to b. 3 over 6th root of x. Okay? So b is under my control. I'm going to go through this process that we evaluate definite integrals, but I'm going to control that upper limit, eventually pushing it to infinity. Okay? All right, so if we go through our typical procedure of probably writing this like 3 times x to the minus 1 over 6 power. That's the form we would put it in to find the antiderivative. Then this is what we're going to get when we work on this to find the antiderivative. Limit b goes to infinity. And then we'll get in there 18/5. And this will be the 5 over 6 power. Okay. There you go. All right. So now the limits of integration go in, but the b goes to infinity once we have that established. Okay. So it's going to look like this. Limit b goes to infinity. All right. B here. So 18 over 5. B to the 5 over 6 power minus 1. All right, 1 to the power 5 over 6 you could calculate to just be 1. So it's going to be minus 18 over 5. Okay. Now, all right, this power is a positive number. All right. And the larger I make b, the larger b to the 5 over 6 power is going to calculate. All right, so the larger b is, the larger this number is without bound, it goes to infinity. 18/5 times b to the 5 over 6 power as b goes to infinity, that goes to infinity. So I'm going to get infinity minus 18/5. Well, that's just infinity, right? This number is getting larger and larger, so we just subtract 18/5. You know, at some point you're going to take 10 trillion minus 18/5. That whole thing is headed to infinity. All right, now, it turns out the graph of this one looks similar to that one. I mean, if I drew them side by side to scale, they would look a little bit different, but they both have this horizontal asymptote. From 1 to infinity, it's still unbounded, and there's always this little sliver of area that never quite closes off. It turns out, though, that this one would have infinite size to it. Its area would be infinity. So we could say that the value of this integral was infinity. The term that's often used, though, is to say that the integral diverges. Okay? So depending on who you ask, They might prefer one form of answer over the other. So I'm just going to put them both there and tell you that they're interchangeable. Okay? So infinity means the integral diverges. It means that this space actually does have infinite area to it. Unlike in this one, its graph, the area was 1/8 of a square unit. Right? So you see the difference. Now, that's what's going to happen with the improper integrals. We'll set them up and we'll work them. You know, they're all a little bit different as far as that goes. But we either get a finite number or we get infinity or negative infinity. That's the difference between the integral converging or diverging. All right? So they're all going to work one way or another like that.